A circle begins as a single coordinate in space. From that solitary anchor, a fixed distance sweeps outward, carving a perimeter of absolute symmetry. This is a garden fountain, but beneath the water and stone, it is a physical manifestation of strict mathematical rules. Today, we are examining the definitive geometric relationships between straight lines, individual line segments, and the circles they interact with them in physical space. We will break this analysis into two distinct domains. First, we will examine the internal mechanics of individual line segments cutting through a single circle. Second, we will expand outward to map the external multi-circle interactions taking place across a shared plane. Every calculation we make relies on one absolute reference point, the circle's center. This mathematical anchor is required to prove all internal measurements and geometric theorems. To master the geometry of a circle, you must stop looking at the continuous curve. The structure of any circle is entirely governed by the straight, predictable lines that define its limits. We begin inside the perimeter by defining a chord. A chord is any straight line segment that connects two distinct, separate points on the outer edge of a circle. Examine this diagram illustrating Theorem 6.3.1. A line drawn downward from center point O at a 90-degree angle bisects chord TV at intersection R. This bisection continues outward, splitting the curved boundary into two equal arc segments between points T and V. Theorem 6.3.2 provides the strict converse to this rule, reversing the mathematical logic. If a line passing through the center point divides any chord into two equal halves, the resulting intersection between those lines must mathematically be exactly 90 degrees. This brings us to the final rule in this triad, Theorem 6.3.3, which formally defines the term perpendicular bisector. It dictates that the perpendicular bisector of any given chord, regardless of its angle or placement within the boundary, forms a direct linear pathway that will always contain the true center point of the circle. These theorems prove a circle's interior isn't a shapeless void. Using perpendicular intersections to locate the center constructs a structured grid of rigid right triangle relationships. We can now apply these theorems to solve a practical geometric problem, calculating the exact total length of a specific unknown chord when we only have the circle's radius and the shortest distance from the center to that chord. Look at this technical diagram. Circle O features a radius of 5, and a perpendicular line dropping to the chord has a length of 3. Connecting center point O to point C constructs a complete right triangle, OBC. Because we have constructed a right triangle, we apply the Pythagorean theorem. We square the hypotenuse, our radius of 5, resulting in 25, and subtract the square of the vertical drop, 3, which is 9. The difference is 16. Taking the square root proves that the horizontal half-chord segment BC equals exactly 4. Now we apply Theorem 6.3.1 from our previous rule set. Because the center line drops at a perpendicular 90-degree angle, we mathematically know the established segment BC is exactly 1/2 of the total chord length. By multiplying the segment BC by 2, we reveal that the final total length of chord CD is 8. Drawing abstract perpendicular bisectors is the primary mathematical method engineers rely on to extract precise linear dimensions from unmeasurable continuous curves. We shift our theoretical focus from the internal mechanics of a single circle to the coplanar relationships governing multi-circle systems. The simplest multi-circle arrangement utilizes concentric circles. Concentric circles are distinct rings of different sizes that orbit a shared, identical central coordinate point. This diagram highlights a unique intersection in concentric systems. The straight red line rests tangentially on the blue inner circle, while simultaneously functioning as a chord cutting through the black outer circle. We must apply a different taxonomy when discussing tangent circles. Tangent circles are defined strictly as two distinct circles that physically touch at exactly one singular microscopic point. There is a spatial difference between internally tangent circles, where one shape is entirely nested inside the other, and externally tangent circles, where the two shapes touch strictly from the outside, meeting edge to edge. Whether circles share a center point entirely or merely graze distinct edges, their formal mathematical classification relies entirely on mapping the specific location of their central axes. When mapping a two-circle system, the foundational metric is the line of centers. The line of centers is the primary invisible axis spanning the spatial gap to directly connect the exact center point of circle A to the center point of circle B. From this axis, we introduce the concept of the common tangent. A common tangent is a single straight line capable of grazing the outer boundaries of two entirely separate circles at the exact same time. The spatial interaction between the tangent and the line of centers provides a rigid classification, starting with the common external tangent. A common external tangent will span smoothly across the extreme outer edges of both circles without ever crossing or physically touching the central invisible axis connecting them. The opposing spatial rule dictates the behavior of a common internal tangent. Internal tangents must squeeze tightly between the circles, violently crossing the line of centers to form an intersecting X pattern in the open gap. The line of centers operates as an invisible, unbending border that mathematically categorizes the position and behavior of every tangent line that touches the system. We have established the micro-level internal mechanics. Creating perpendicular relationships between center points and chords grants us the ability to extract precise geometric lengths via right triangles. We have also mapped the macro-level external mechanics. Across complex structural systems, the line of centers serves as the ultimate reference for dictating tangent behavior. Contrast the single-circle chord problem against the multi-circle tangent problem. While they operate at different scales, both rely on the exact same structural logic, demonstrating the scalable consistency of these geometric axioms. Circular geometry is merely the illusion of a continuous curve. It is entirely dictated by an underlying scaffold of perfectly straight lines. Mastering these specific axioms provides the foundational mathematical vocabulary required to solve advanced spatial, mechanical, and engineering problems across any physical plane.